If your model keeps missing the important class, the loss function is often the real problem. This is the setup you'll be able to run after this, which trains on imbalanced labels with focal loss, and then flags rare positives with credible scores. I'm Professor Pi, teaching AI foundations with simple Python. Most classification projects are imbalanced in the real world. Think fraud detection, rare disease screening, or defect spotting in manufacturing. You can have thousands of negatives and only a handful of positives. Standard loss functions can wash out the signal from those few positives. Success means the model notices and improves on the rare cases while keeping overall stability. Focal loss is a simple change to the loss that pushes learning toward hard, rare examples instead of the easy, abundant negatives. PyTorch is a natural fit because it gives per-example control over loss and gradients, so we can experiment quickly. Intuitively, focal loss downweights easy examples and amplifies hard ones. Imagine most negatives sit far from the decision boundary and cost almost nothing. Focal loss says those easy points should count less. The formula multiplies the baseline loss by a weight that shrinks for confident predictions and grows for uncertain ones. Strengths: better recall on rare classes and simpler training than complex sampling schemes. Weakness: you must tune two knobs and watch for overfitting the minority. We will build a tiny diagnostic and training pipeline. First, we will measure how much of the plain loss comes from positives on a toy imbalance set. Then, we will implement focal weighting and compare which samples each loss considers hardest. Finally, we will train a one-feature linear model with focal loss and inspect the minority recall. This keeps the math light and shows direct effects before you scale things up. Now we will measure the imbalance effect on plain binary cross-entropy. This snippet quantifies how standard PyTorch BCE spreads loss across classes on an imbalanced toy set. We seed for determinism, then create logits that mostly favor the negative class and labels with only a few positives. The object BCEWithLogitsLoss, with reduction set to none, returns a per-example loss tensor L, so we can analyze contributions. We sum losses where the variable y equals 1 and divide by the total to get pos share. This reveals how much of the training signal comes from the rare class under plain BCE. A small pos share indicates positives are underweighted, explaining why rare cases get missed. Next, we will implement focal loss and compute how the loss redistributes. This example applies focal loss in PyTorch to reduce the impact of easy negatives and spotlight hard positives. We compute probabilities with torch sigmoid, then form PT as the probability aligned with the true class by using torch where to pick P for positives and 1 - P for negatives. The variable at encodes class weighting via alpha for positives and 1 - alpha for negatives. We build the focal weight W by raising 1 - PT to the power gamma, then multiply by AT, and form the focal losses FL using a stable log expression so the numbers stay well behaved. Finally, pos share focal reports the positive share of the total focal loss. A higher pos share focal confirms the reweighting favors rare, hard cases. Now we will compare which samples each loss treats as hardest. This code compares which samples are prioritized as hardest under PyTorch BCE versus focal loss. We select the indices of the top K losses using the top K operation on the BCE losses L and on the focal losses FL. The variable top B holds the hardest examples for BCE, while top F holds them for focal loss. By summing the labels Y at those indices, we count how many positives each criterion elevates into the hardest set. The difference delta shows how many additional positives move into the hardest set under focal loss. A positive delta implies focal loss is shifting attention toward minority errors that standard BCE might overlook, which is exactly the practical goal when positives are rare. Next, we will test how the focusing parameter gamma changes that attention. This snippet tests how increasing the PyTorch focal loss focusing parameter gamma shifts attention. We recompute the focal weights W2 by raising 1 minus PT to gamma 2, keeping the same class balancing at. The new per example focal losses FL2 are built with the same log expression for numerical stability. We then compute gain as the change in the positive loss share between FL2 and the earlier FL. Larger gamma strengthens emphasis on misclassified and uncertain examples. Smaller gamma relaxes this effect and behaves closer to BCE. A positive focus gain means a higher gamma concentrates even more training signal on positives, but very large gamma can ignore medium difficulty examples and destabilize training. Now we will train a minimal linear model using focal loss to see learning behavior. This snippet trains a minimal PyTorch linear model with focal loss to nudge learning toward rare positives. We create a one-feature input X from the earlier logits plus small noise for realism. The torch NN linear layer outputs logits that we convert to probabilities with torch sigmoid. Inside the loop, PT is the probability of the true class, and the focal expression uses the previously defined AT and gamma to weight hard examples more. We optimize using torch optim SGD with a modest learning rate for a few passes. Tuning alpha higher or gamma larger further prioritizes positives but may overfit. The printed recall shows the minority hit rate after training. If you map this toy to a real system, treat the one feature as a single signal among many. Replace the linear layer with a richer network and replace the toy labels with your dataset labels. Keep focal loss as the same reweighting idea and observe whether recall on the rare class improves without destroying overall calibration. Recap. Focal loss is a reweighting of the baseline binary cross-entropy that downweights easy examples and highlights hard ones. Use it when positives are rare and you need higher recall on those minority cases. Caveat: you must tune alpha and gamma and monitor overfitting and stability. Next step: tune gamma and alpha on a validation fold and plot positive loss share versus epoch to pick a sweet spot that improves recall without exploding variance. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.